I'd like to introduce our last plenary speaker, Bruno Lévy. So it's a real pleasure for me to have Bruno here. We kind of did our PhD together. He was a little bit before me, but he taught me a lot. He's almost be like a grandfather, not father, like a big brother. Not the big brother overseeing every gesture you're making, but more big brother bringing you upward and helping you. So in a sense, this is a very biased choice for a plenary lecturer, and I apologize for that, but I hope you won't regret. He did his PhD with Jean-Laurent Mallet in 1999, and it was a PhD in computer science, and he was working on parameterization of surfaces to solve grading problems at the time. And then he went completely into the computer graphics, and now he was telling me over lunch that he's no longer a computer graphics guy. Well, maybe still a little bit. But he's trying to use applied mathematics and computers to solve physics problems. So I'm not sure how much geoscience will be in this talk, but I guess that's also one of the interesting things of mathematical geoscience. We can be anywhere moving the cursor between computations, mathematics, and geosciences, and so we're in this ternary diagram somewhere. And I hope that, I'm sure that this is going to be a very exciting talk, and so thank you so much. Bruno, I should mention that he's now the INRIA Center Director for the center in Nancy. So he has a busy schedule, but he's still having fun doing some research, so this is great that you're here. Thank you.
So thank you very much, Guillaume, and so it's a great emotion for me to have the opportunity to present you this work. So this afternoon I will be talking about optimal transport. There was already this word already appeared in different presentations here. It's a mathematical tool, and so here I will try to give you a different perspective on this tool and some of its relation with physics, because there are close connections. And so imagine you are in your garden, you are watching the stars, and then you got a sensation of vertigo, of the scales are huge, and maybe you can start wondering what would happen if I could unzoom everything and make the width of the image get larger and larger and larger. Would there be structures? What would it look like? I'm wondering. Or you can wonder what would happen if I could turn back time and did these stars have always been there? How did they move? And so you can ask these sort of questions. And maybe you can wonder, what do we know? What do we know about the sky? What do we know about the universe? And in fact, we know different things. We know a lot of things about gravity. We know a lot of things about light. But there are still some mysteries, and big mysteries. One of these mysteries, it was discovered by Vera Rubin, maybe 50 years ago. She was watching galaxies, and she established a large number of curves. And in these curves, the x-axis is the distance to the center of the galaxy, and the y-axis corresponds to the speed of the stars. And she noticed that the stars, they turn too fast around the galaxies. Too fast with respect to what? Too fast with respect to the galaxies being stable. Normally, if the stars go that speed spin around at that speed, the galaxies shouldn't be stable. So and in fact, she came out with an explanation, a possible explanation, that there is more mass than what we observe. And if there is more mass, it makes the galaxy, thanks to gravity, it makes the galaxy stay together and not going like that in the cosmos. And in fact, there is more mass, so it's a possible explanation. Is it true? Is it false? We don't know. But there is another hint that there should be more mass. You probably all know about this picture, the very recent one. There's James Webb Telescope that produced this image. It's an image in very, very, very deep space. And if you look at this image, you can observe that it seems to be distorted. And you see two bright galaxy clusters near the center, and around the center, the galaxy seems to be elongated. And so it's an effect of what is called gravitational lensing. And you know that gravity deforms space-time, and light travels along the geodesics in space-time, and so the deformation of light causes this. And so you can compute the amount of mass that is due to the gravitational lensing, and there is also more mass in there. There is also more mass. So it's one of the mysteries. There is another mystery, and in the end of the 90s, the astrophysicists, they have seen that, with my own word, the Big Bang is Big Banging faster than we thought. It's getting worse and worse. It's accelerating. It's the past few billion years, the expansion of the universe accelerated. How do we know? We know because some very special supernovae, there is a relation between their brightness and their distance. So we should have like landmarks in space and measure the distance, and they are much, much further away than we thought. And then we could determine that the expansion of the universe is accelerating. And also, so you see the last few billion years, so it gets this acceleration, the expansion of the universe accelerating. And so, so these two mysteries, two categories of mysteries. So yes, we have words for saying that, but they are just words. We say that there is more matter, but we don't see it. They observed in all possible wavelengths, they found nothing. And so they said it's dark matter. It's just a mean of saying that we don't know what it is. Maybe it's not even matter, by the way. It could be the laws of gravitation that do not work the way we think. And about Big Banging faster than we thought, and they call it dark energy, but we don't know what it is either. So how do astrophysicists try to shed some light on this problem? Well, they have theories, they have models of what happened. So first you got Newton's equations, it's the basis of everything. So there's the first law of Newton saying that if there is no force, everything will travel along straight lines at constant speed. If there is a force, then you got the relation force equals mass times acceleration. And for gravity, the famous formula of Newton, product of masses divided by square distance times the constant, this g constant. Okay. Then you got general relativity. General relativity, in a certain sense, is like Newton's law, but you only keep the first one. You say everything moves along straight lines always. But you change the definition of what a straight line is. So you got in formula, so there is something that contains T mu nu, contains the mass and energy content of the universe. And this G mu nu is geometry, and it's a definition of what a straight line is, and it's a curved straight line in a certain curved space, and that makes the trajectories bent along the matter. And in fact, so because of dark energy, what we observed, they needed to resuscitate a term that Einstein had dropped in the equation. This is this lambda term, and that makes the expansion of the universe push a little bit harder to account for this acceleration. But we still don't know what it is. And that's clear. So we got these different models. There are other models changing the laws of gravity, modify Newton dynamics, or other theories. And then, well, you can have as many theories as you want. The equations can be as elegant as they are. Feynman was saying, if it does not match the measurement, then your theory is wrong. That's super important. So you need to confront your theories to observations. So what are the observations? You can have 3D map of the universe that looks like that, and you use a telescope and look up the position of a large number of galaxies. You see there's some grain, it looks like some bread or some fibers or things. I will talk a little bit about that later. So it's reproduced in simulation, good sign. It means that if we put the equation in simulation, make them evolve, we see something that looks like the observation. It doesn't prove anything, but at least it proves that there may be some truth in these models. It looks like also what you see in a swimming pool. There is a reason for that. I will talk a little bit more about that, but much later in this presentation. Okay, so it's the first type of measurement, 3D maps of the universe. And you can also make another measurement, which is the cosmic microwave background. So it's some light that was emitted very soon in the life of the universe, 380,000 years after Big Bang, that we are still measuring today. And so it has very small fluctuations that are mapped here, and it contains information about the history of the universe. So the idea is to confront the models with these two sources of information. And so we got a source of information that's a 3D map of the universe now, and we got this fossil from the past, which is the history of the universe, almost 7 billion years ago. And so we need to, in a certain sense, connect the past with the present. But it's more complicated than that, because the 3D map of the universe, the further away you look, the more in the past you look. And so, in fact, this map is like a cross-section in space-time, and you need to take that into account. Then the idea would be, how can we connect the present to the past and test these different models to know which one is more true or more false than the other, and maybe come out with other models. So what are the equations? The equation, so I will start one element at a time. So first thing is Newton gravity. I've got a big mass, capital M, at the origin, a small mass, small m, somewhere else. R is coordinate of the small mass. And then the small mass feels the force, F of R, which is the famous formula by Newton. And then this formula is the gradient of a potential. It's super classical. And this potential, you just integrate the previous equation, you obtain the formula for the potential. Okay. But now what happens if you got a larger number of particles? Then you will feel a force MI/GI. This is just the sum of the forces over all the other particles. And it is also the gradient of a potential, which is the sum of the potentials for all the particles. And then if you put that in a computer, that's an n-body system. And you can, the simulations I was showing, they were generated by some forms of this equation. But now we are considering the universe at a very, very large scale. And if you look at the universe at that scale, all the galaxies and stars and clusters, you just see like a haze, and it becomes like a gas with a varying density. And so you want to write the equations more in Eulerian form, in fields, and how density with respect to position and time evolves with respect to time. So how do you do that? You still measure the force received at a position in space, and you write the Newton law, F equals ma, and then the F is still the gradient of a potential. And this potential is a sum over all the positions, then it becomes an integral. And then you say, okay, so I've got this equation, but I don't like it very much because there's this integration over the whole space. And I want to do physics. In physics, you know, it's a language of differential equation. You like to connect variations with respect to time with variations with respect to space. So this is something that is very local. And here we got something that is very global. But there is something, there is a trick. If you look at this equation, in fact, you can recognize something which is a fundamental solution to the Laplace equation, which is, this K here. And the solution to the Laplace equation is a convolution between K and the right-hand side of the equation. And in fact, this is exactly what we have in the expression of phi, convolution of rho with K. This is K. And then, by recognizing that, you know that the potential satisfies the Poisson equation, Laplacian phi equal 4 pi g rho. Where does pi comes from? Well, it comes, you know, there is an exponential in there, and exponential and pi, they fit well together. Okay. So now you need to write acceleration. Acceleration, derivative with respect to space of the velocity, but here we are in Eulerian, and we are considering fixed point in space. And so when we go from t to t plus delta t, the point under the location we were watching has changed, not the same point. You need to take that into account, so there is this u nabla u that takes care of that, and then you get this equation, this second equation, and we know that Laplacian of phi equals 4pg rho. But it's not sufficient, because now we got two sets of variables to represent our system. There is the velocity, there is the density, but you cannot. Not every velocity will go to every density. They need to have a compatibility condition that says that mass is conserved. This is a continuity equation. Okay, so you need one more little thing, is that the universe is expanding, and if I'm considering a small chunk of universe, here, my little square, and over t, this small chunk will become huge. It goes like that, and there is a side of this square with respect to time. It's called A of t, the expansion scale factor. And if you take the relativity into account, but at a quite coarse scale, you can write an equation that conditions A. And then there are several solutions to this equation. You take a simple one, supposing a space-time is rather flat, then you can have the evolution of A of t. And then what we are going to do, we write everything is this little square. Now we fix it. Imagine this is the screen of your computer. And then you cancel out the expansion of the universe. And by cranking the algebra, writing the equation, we end up with this system of equation, very similar to what we have done before, except the circle terms. You see, there is 3 over 2 tau, and here we divide by tau. Tau is like time. It's not really time, but it's another time. We changed the time, and so now you got the equation of the evolution of the universe at a certain scale. So what is our task now? Our task, we got the data. The data is like a 3D map of the universe to the right. We got the initial condition that we're supposed to be homogeneous. There are two reasons for that. A bad reason and a good reason. The bad reason is that if you look at the last equation, Laplacian of phi equals 4 pi g rho minus 1 over tau, I divide by tau, and at tau equals 0, if the numerator is not equal to 0, I'm dividing by 0, which is not allowed. So it means that rho equals 1 at the beginning, constant density. So it's not good reason, because nature doesn't care about our equation. And so the other good reason is that the measurement of the cosmic microwave background that we make is super homogeneous, 0.001% of variations. This argument is more legitimate than the first one. And so we want to inverse this equation to reconstruct the history of the universe from the 3D map. How can we do that? Well, there is something simpler we can do, which is called, because here we want to optimize something, minimize something. And in fact, so this is the least action principle. Another way of writing the same equation, the generalization of the well-known things like electricity travels in the shortest path, or the light takes the fastest path, Maupertuis principle, and there is a generalized version of that with respect to space and with respect to time. Then you can write the same equation as before, but in the least action form. And it says that something is minimized. For a computer scientist, it's simpler to minimize something than to solve something with respect to starting and ending boundary condition. It's more difficult. Here I'm just minimizing something. And since, but these 3/2 to 3/2, they are a bit complicated, so I will make it simpler. I drop them, sorry about that, and I'll take just the kinetic energy, rho v square, integrated kinetic energy with respect to space and to time, trying to minimize that with the boundary conditions that the starting and the ending condition match. How can we do that again? So if you minimize the kinetic energy for one particle, then you will find that these particles travels along a straight line with constant speed. And in fact, it's still the case for multiple particles. And then what we have to find, now we got the trajectories of all particles, but we don't know which particle goes where. And this is what we want to do. And this is like an application T of x that tells you where x goes from the initial to the final condition. And so there is a very nice theorem by Benamou and Brognier that makes time disappear from the equation. There is no time. So on the right equation, you just say that you should minimize the integrated squared lengths of all the traveled distances. Another way of saying that, if you are in a discrete world with discrete particles, you just compute the coupling between the initial and final positions that minimizes the sum of the squared travel distances. And so now, how can we do that? We will still keep the two versions, continuous version and the discrete version. Discrete version, you could enumerate all possibilities. You got factorial n. It's a bit too much, but there are algorithms that work. N squared log n, still a lot, but it's doable for 10,000, 100,000, it's still doable. But there is a limit, 100,000, more than that, it's going to take months on a big computer. But the continuous one, we can exploit it. So now, how can we compute this optimal transport? So remember, there is a continuous version. So you got like a gas. Imagine a gas. It has an initial repartition, density with respect to position, and you got the final density of the gas. You want to compute the way all the gas molecules did traveled along straight lines. So in terms of mathematical language, it's not a gas, it's probability measures, mu and nu. You got the same quantity of gas on the left and on the right. There's a condition among all the movements you will compute, is that mu, so what does it mean? So let's see that intuitively. The condition says that if you take a blob, if you consider a blob B in the right part of the image, you back project it through the inverse of the mapping that you are computing, it should contain the same quantity of matter. This is like a matter conservation constraint. So it's a transport map if this constraint is satisfied. The constraint is for any subset of Y, any subset B of Y, T-1 of B should contain the same quantity of matter as B. This is the constraint. And now, I have to program that. How can I do that? The constraint is crazy. Imagine that for any B. But there is a trick. Okay? So the constraint is crazy. And the trick is Kantorovich. Kantorovich came maybe so, and okay, so he got this equation. What does it mean? So let me do some drawings, better understand drawings, that equation. I will do a drawing in 1D. Because, and in 1D, so I've got still my gas as initial position, which is mu. It has this density profile. Gas at finite position, nu, with this density profile. Then I want to know where each particle goes. One way to picture that is to put mu on the x-axis, nu on the y-axis. So I'm going to create a table of values. This table of values will tell me where xi goes, so I project it onto this graph, and it tells me that it goes to y. So it's a nice way of drawing the graph of t in a certain sense. And so the idea of Kantorovich was saying is to compute the graph of t, instead of computing t, our unknowns will be like an image of t with all the pixels. So it does that in a continuous manner, and so there could be values everywhere else in the image, and they are not necessarily 0 and 1. So what does it mean? It means that each square of the image tells you how much matter goes from mu to nu. And so these are our unknowns. A bit crazy because I've got n values for mu, n values for nu, and now I'm considering that in a discrete manner. It also works in a continuous manner. It's easier to think about in a discrete manner. And you get, okay, these values, pixel values, I will call them gamma ij, and that gamma ij tells you how much matters go from I to j. You cannot take arbitrary gamma values. They need to satisfy some constraints. So the constraints, so yes, gamma is the vector of all the colors of my pixels in the image. I put them in a vector. I can arrange them like that. There is this C vector. This is the vector of all distances between the points. It's a fixed vector. They are not variables. Huh? This is gamma that I'm looking for. So distances. And my constraints. My constraints, what they say, the first constraint will say that everything that comes out of I should sum to the quantity of matter I initially had in I. I cannot send more matter than what I have, and I'm obliged to send all the matter that I have. And the other constraints say that the matter I want to receive at a certain position is also constrained. These are the two constraints. And also, gamma should be greater than 0. You don't want to generate or do some tricks with the matter. Third constraint. But here I got a problem. I want to program this stuff. I got maybe, I don't know, in the biggest simulation, I have 300 million points. And so here I'm talking about a problem with n square unknowns. 300 million squared makes a big number of unknowns. What can we do? Well, there is a trick, the trick by Kantorovich, which say, okay, I've got n square variables, but I've got n constraints plus n constraints. Constraints on the rows, constraints on the columns. And this works also in 2D, in 3D, etc. But so there is a trick where you can switch the constraints and the variables. Because if I've got n square constraints, so it's okay if they are simple. But if I go from n square variables to 2n variables, it will be cool. So there's a bit of algebra. I will maybe go a bit faster through that, but you construct a special function like that. Don't try to justify it from now. Take it like that. And you can show that this function is such that the inf with respect to gamma of the sup with respect to two functions with n coefficients that you have defined is the solution of your optimization problem. Because you want to minimize, remember that, you want to minimize the traveled square distance with respect to sum over the rows equals what you started from, sum over the columns equals where you want to land. And in fact, this function you can switch the inf and the sup. So with vectors, it works like that. With functions, you take more care, but there are nice theorems that allow to do that due to Rockefeller. And once you have done that, you do a little bit of algebra, and you get another expression, and then you can wonder, what does this expression mean? And this expression is another constraint optimization problem, which is now we wanted to minimize something, now we want to maximize something. We want to maximize something that is the dot product between a function phi, or n coefficients phi, with the distribution we start from, plus the dot product of another function with the distribution we want to land to, subject to a constraint that says that for each pair of points, the function phi at the first point plus psi at the second point should be smaller than the cost between the first and the second point. So the second problem, we got 2n. We started from n square unknowns, now we got 2n unknowns. Cool. We can imagine programming that. And in fact, it's even better than that, because we can get rid of half of the variables. Because phi and psi, they are connected with a relation. And this relation, in physics, it's well known. This is Legendre function transform. The very transform that goes from Lagrangian to Hamiltonian representation in the minimum action principle, or the relation between entropy and enthalpy in thermodynamics, something very well known, but in fact you can get rid of half of the variables. So now, how can we program that in our case? Well, in case you want to try it, to play with it, there is everything in my GitHub. You can download all the source code or a Windows binary version if you want to play with it. And there is a tutorial page for, and then you'll be able to redo the experiments, compute your own optimal transport, and play with it to do fluid simulation. Okay, so you got different version of the optimal transport problem. There is continuous to continuous. There is semi-discrete, continuous to discrete, it's interesting, and discrete to discrete, of course. But here we will focus on continuous to discrete. Why? There are two reasons for that. Because this is the very configuration we have to study. Initial condition of the universe, uniform. So it's the Lebesgue measure. And configuration now, we got a set of galaxies. At that scale, we can model it with Dirac distributions. And now you want to compute the transport between this and that. You just write the formula, and here you got nothing to invent, because optimal transport theory, it's written in a very general language. It manipulates probability measures. They are very general objects that encompass standard functions, but also a sum of Dirac. It still works with a sum of Dirac. And if you just write the formula in this context, you will see the second term, it becomes just a sum of dot product between a vector that I wrote psi of yj, but I could write it psi j. This is a set of n coefficients. And this guy, the first term, I said this is the Legendre transform of the second one. So I denote it by psi c. And if you write the equation of the Legendre transform, you get in the integrand, you got, so this is the Legendre transform. You can reorder the terms. And if you reorder the terms, it will decompose the domain into regions. The regions correspond to where the inf of the formula is attained by one of the j. And so it's something called a Lagarde diagram. So this is where Lagarde diagrams enter the scene. They come from the Legendre transform of the discrete probability measure on the right. Okay, so now we know what we want to minimize. The formula with integrals over the Laguerre cells, and then we can come with an algorithm. What will this algorithm compute? It will compute psi. Psi that can be represented by a vector of n coefficients. But what does it mean intuitively? Intuitively, this is just this formula. I like to do drawings. So imagine you start by a Voronoi diagram that you draw on a transparent sheet of paper. And imagine that the psi, they correspond to by how much you lift the points. Here I'm lifting my Voronoi diagram. And when you do that, you can see that the shadow of my drawing is moving away and deforming. And so I'm lifting, it's deforming the shadow. So it's interesting. And so you can think of different ways of, can I translate a Voronoi diagram to an arbitrary position by lifting it? What is the formula of the lifting? If you just tilt the transparent sheet of paper, it won't be good because you will introduce a 1 over cos alpha, which is the angle, the tilting angle, and it will deform the drawing. But if you want to just translate, you need to curve a little bit your sheet of paper, and curve by a square root function. And so you can do the computation, and it tells you how to translate, to do a translation. And you can imagine that by combining different translation and curving it in different ways, you can also deform the Voronoi diagram. And this is exactly what optimal transport computes. It computes the optimal deformation of this sheet of paper, correspond to psi. It also corresponds to the gravitational potential. By the way, what to compute is the gravitational potential. And so how does the algorithm work? Well, what you have to do is minimizing a function, but this function is very nice, in fact, because it's convex, so there is a unique minimum, and it's smooth, it's C2 continuous. So you just do a Newton algorithm. There is a little thing you need to do. I said that gamma ij needs to be positive. This is a tricky constraint. Gamma ij needs to be positive. And so here, what it means that all the cells of your diagram should remain non-empty. Because in a Laguerre diagram, you can end up with empty cells. And this you don't want to have because this would violate the constraints, so you need to control the step length in order to avoid that. There's a very nice algorithm for that due to Yoon Kitagawa, Quentin Merigot, and Boris Tiber, who are good friends of mine. Okay, and so what does the algorithm do? It starts with the Voronoi diagram, and so you see that here it's wrong because all the points were supposed to have the same mass, and what we draw here is the region of the initial universe that it collapsed in each point. And here there should be the same amount of matter for each point. They are supposed, in this example, to have the same mass. So this drawing is wrong. Then the algorithm will optimize it again, and again, and in the end, all the cells have the same area. You can see there is a lot of anisotropy in this diagram, but this is normal because the movements in the universe they were quite violent to create these densities of matter. So now I will show you some results and conclude. So first, 2D results, same result as before. So here it's a synthetic result. I'm started from a simulation. And so here, what I'm showing to you, this is my transparent sheet of paper that I was showing before, computed. This is a plot of the psi function. In fact, the Legendre transform of the psi function. It's about the same thing. And so what it means, now if I want to reconstruct the trajectories, what I'm doing, so I will project each point onto the surface, and then reflecting, not really the laws of reflection, but reflecting following the normal vector to this surface. This is because t is equal to the gradient of phi. So following this normal vector, and it will cross the z equals 0 plane again, and it tells you where the point lands. And so if you look at that from above, you can see the trajectories of the points, and and it can plot like a fireworks or like the explosion that landed to this configuration. And so if I go back to this image, do you remember my swimming pool with the pattern? What we compute with optimal transport, in fact, this is the equation of the surface of the water that will create a certain pattern at the bottom of the swimming pool. This is, this is the surface displayed in gray here. Okay. Now a 3D result. So a 3D result, we did that on a computer simulation, still computer simulation, with 300 million particles. We could compute a gigantic Laguerre diagram. Here I'm showing just a tiny portion of it. Here I am zooming in, it's a tiny portion of it. So it's stored in a very compressed manner in the computer. And then after a few hours, a big PC, we can reconstruct the transport. And so we can do something. Then the question is, do we have computed something that has a meaning? Maybe it's nonsense, I don't know. So we need to find ways of proving it's nonsense. It's always in that direction. And so in fact, my friends, they did hide a signal in their initial condition, gave me the final condition with a signal that was blurred a lot, and testing my code whether it was able to reconstruct this signal. And the answer is yes, it's able to reconstruct this signal with a good accuracy. It's not a proof that it worked, but at least if it had not worked, it would be a proof that everything is broken. So it's very encouraging. So what is this signal? It's it's like sound waves that traveled in the very early universe. Not really sound, but like pressure waves, very similar to sound, that created some structures, some patterns that we can still analyze statically today. We can reconstruct them. So let me just show you a couple of images of other things you can do relating optimal transport with physics. Yeah. So you can simulate fluids with that. Probably not the best way of simulating fluids, but I like it because it's a purely Lagrangian fluid simulation for fluids with free surfaces. You can do that with SPH, for instance. There are several talks about SPH in this conference, but you can do that also with optimal transport, and you can create nice splashes like that. And so particularity of this method is that you can have strong topology changes of the surface. You can accurately model viscosity and surface tension. We have nice expression of viscosity of surface tension, and you can see that. So one slide about what's next. What's next? What's next is playing with these equations to see if we could find some small variations that could lead to more accurate predictions of what the universe is doing. And so there is one possibility, it's Jan Bronier's idea, that is, if you take the equation we had, there was Laplacian of phi equals 4 pi g rho minus 1 over 2. This is the third equation here. What you can do, you replace the Laplacian by something else, which is MA. It stands for Monge-Ampère. This is the Monge-Ampère operator, something that comes from optimal transport. This is the determinant of the Jacobian of the gradient of phi. And if you take that to the second order, you retrieve the Laplacian. So it's interesting. It's a higher order generalization of the previous equation. And if you simulate that on a computer, this is the result by Pierre Boldrini, who is a postdoc at Institut d'Astrophysique de Paris. It's very encouraging because the distribution of the small galaxies seems to better match what we measured in reality. So we are quite excited by that. So of course, the next step will be also to apply the method to observational data, redshift acquisition survey, so it requires a lot of work to do that. Okay, so before I finish, I wish to thank all the people who have been working on this project since 2015, and so I met astrophysicists and mathematicians on that. And I wish also to thank two friends. So it's always nice for me to have friendly faces in the public, but I want to show their faces to you. And so we had many discussions, including this morning with you, Jean-Laurent, about that topics. And so I'm very, very happy that you are here, and thank you for that. And one last word. So I deeply think that interesting discoveries, super interesting discoveries, are to be made at the boundary between different disciplines. We need to connect disciplines. And I think that the logo of the IAMG is a super expression of that. I love this logo very much, and I love also the fact that you kept a punch card on this logo. It's so funny, I love it. So thank you very much for your attention.
Thanks a lot, Bruno.